We have this world of system modeling, the Wolfram System Modeler, that is a framework for building and simulating with large complex systems of components, where components can be dragged from libraries or created from scratch. So a circuit diagram is a classic example. And here's a circuit diagram. I've got some resistors and inductors and a power source, and they're wired up in some complex way. And System Model lets you help design those things. The simulation of those, once they're built, any Modelica model that is compatible, we can just treat as a black box that represents the circuit. So that in the Wolfram language world, this thing is pre-built. I could try and program in the Wolfram language, but it's not really designed for that. And I've imported the model as a black box. So just like I've got functions like sine and cos, I've got circuit. I've got Cauer low-pass analog circuit as a function now that I've dragged into the system. So we've had for a while the ability to do things like tune those to fit the parameters to experimental data, to simulate them, to plot how they different parameters behave. What we're bringing here is model validation. So what do we mean by that? Well, we build a circuit, but does it work? Well, what does it work mean? So you need a language to describe that. And the language really breaks down at the moment into these sort of 5 paradigms. We want some property to always be true. We want some property to remain in some state. We want some property doesn't have to be true at the beginning, but we want it eventually to become true. And the opposite is we want something to be true until something else happens. And we also want to have a way of playing around with time. So what we mean as from and until can be manipulated. And between those things, we can set up a set of rules that we say the circuit is expected to behave under. So here's my simple example. I've said system model always. So for all time, the voltage across resistor number 2 has to be less than 0.55 volts. So in my fictitious example here, this resistor will burn out at 0.55 volts. So the circuit will fail, the resistor will get burnt out if I ever exceed some voltage that is in the design spec for why I chose to put that resistor there. So we want to know is it safe to assume that this resistor will never exceed 0.55 volts? Well, that can potentially be a very complicated simulation exercise. It's gone away and it's run a simulation. There's various ways of doing this with Monte Carlo. So here I've taken the simplest thing, which is just to start the simulation with its default values. But I could say throw in a million different start points that we might sample from experimental data and say, how often, if I have temperatures of the day, maybe I want to throw it at the historical temperatures for where I'm sat in Oxford to see the different conditions it might be under. But here I've just said run it once, and it said it's failed. Out of one simulation, we had one failure. It succeeded none of the time. And there's various properties we could look at, but I'm just going to throw up a plot here that says, show me, visualizations of the failure. And you can see that most of the time it was in a pass state, but between seconds 9 and 10, it was in a failure state. And if I actually run the simulation, in this case, it's really easy to see what's happened. Here's my voltage in this oscillator circuit. And briefly, it overshot the design condition before stabilizing underneath. And this was what the failure measured. So in a simple thing like this, I would have gone straight to the plot and looked at it and gone, oh, that's gone too high. But in a complex system that's, trying to validate an entire car to say, will this car behave and anything go wrong over thousands of conditions, you can imagine it's impossible just to look at the model and say quickly, is it valid? So now we have a whole language for automating that process.